pleasure to be here. Glad to see so much interest in something that I'm very interested in also. So hope to fill you in on what the Sentinel mission is and how we hope to make it happen over the course of this talk. The Sentinel mission is being pursued by the B612 Foundation. The B612 Foundation was founded about 10 years ago with the intent to look at what would we do if we found an asteroid that was going to impact the Earth. It was founded by Ed Lu and Rusty Schweikert and several other NASA astronauts. And over the course of the following years, they identified feasible technologies that you don't have to nuke it like the movies do, but there are other more controlled ways to deal with a threatening asteroid if you have a lot of time to advance to it. You won't have to move it very far, you don't have to put much velocity change into it in order for that velocity to build up to a lot of motion over a span of several decades. So by 2010, the deflection techniques were pretty well understood. We'd even run a mission, Ball built it called Deep Impact, where we went and hit an object. That's one of the techniques we used to deflect. But the discovery rate had not really gone along. So the problem now was not what would we do if we found out that one was going to hit the Earth, but the problem is we weren't finding them fast enough to give us those decades of warning that we needed in order to deflect. So B612, a couple of years ago, decided to undertake the task of doing a mission that would go out and find the threatening asteroids. I have a video that I'd like to show you that is narrated by Ed Lu, who's the chairman of B612 Foundation, and he does a great job of it, so I'm sure he'll do it better than I could.
So why B612? B612 is the home of The Little Prince, if you remember the novel from Saint-Exupéry. Now, The Little Prince, he lived on an asteroid called B612, and he was always bemused by adults because adults often fail to see what's really important, even though it may be in front of them. But kids, on the other hand, they often don't have that problem. They naturally look up. And kids love space. And sometimes you need to step back and to understand what's really important, what's important in the long term, you need to step back and see the big picture. So this is the big picture. The Earth does not float out there in a vacuum. It's part of something bigger. We live on a giant spaceship called planet Earth, and we orbit the sun. So if coming up here is the sun, you see the Earth orbiting around the sun. We are part of a planetary system. And we go around the sun along with other planets. And in between the orbits of Mars and Jupiter are asteroids. Now, these are all real orbits, and we are showing you the asteroids in the solar system. The ones in the outer part, that's the asteroid belt. Those are the ones that we are not concerned with. We are concerned with the creatively named NearEarth asteroids because they come near Earth, and these are all the green dots that you see. These are all the known near-Earth asteroids. There's about 10,000 known near-Earth asteroids. These are ones whose orbits cross close to or actually cross directly through Earth's orbit. And those are the ones that occasionally come close to the Earth and occasionally hit the Earth. In fact, an impact in Tunguska, Siberia of about a school bus-sized asteroid, it took out an area about the size of San Francisco. However, we've only discovered about 1% of the near-Earth asteroids. This is what it really looks like out there. There are about 1 million asteroids the size of the one that took out Tunguska or larger. That's really what our solar system looks like. And we travel around essentially in a shooting gallery of near-Earth asteroids. So what we would like to do is to build a map, a dynamical map that shows the locations and trajectories of all these near-Earth asteroids. Because it's important for the long-term future of humanity on this planet to understand where they are. So we're going to build this mission called Sentinel, follow the purple line there. We're going to zoom in on it. We're just going to fly inwards in the solar system. We're going to fly past the planet Venus. There's the spacecraft. It is going to use the gravity of Venus, just like this, to fly past Venus and pull into orbit around the sun. It's a space telescope, and it will orbit the sun interior to the Earth. So let's go back and take a look at the big picture again. The orbit in purple is Sentinel. If you look down here, the orbit in sort of the aqua green is the Earth. So at times, Sentinel will be roughly on the same side of the sun as the Earth, and sometimes on the other side of the sun as the Earth. And that means it will range in distance from planet Earth between 30 million miles and about 170 million miles away from Earth. To give you an idea, the Hubble Space Telescope orbits Earth at a distance of about 350 miles. So we'll be about 500,000 times further from Earth than the Hubble Space Telescope. This is our spacecraft. It's an infrared space telescope. And what it's going to do is scan the skies in infrared. Now in infrared, the skies look different. You don't see the stars as brightly, but asteroids, they shine brightly in infrared because they're warmed by the sun. This is what the sky will look like in infrared. You see the Milky Way and lots of bright moving objects. Those are near-Earth asteroids, and we're going to map them. We're going to track about 500,000 of these things, and we will be able, using our tracking, we will track them accurately enough that we will be able to know their positions at any point up to about the next 100 years. And so we are going to fill in that unknown that we currently have of where all these asteroids are. Because the first step in protecting life on this planet from asteroid impacts is to know where they are. It's also the first step in us moving out into our place in the solar system. Because as you saw earlier, the solar system is filled with these things. And those are the things that are going to be scientific targets. Those are things that are going to be the places where we visit. So if you look at this sort of semicircle here, this white semicircle, that is the field of view, that is the area that Sentinel will be able to scan. If you look at the Earth, there are times as this thing moves around, it will scan, always looking away from the sun. You know, as any kid will tell you, telescopes work best when pointed away from the sun. And what it will always be able to do is look away from the sun. While it flies around the sun faster than the Earth, it will scan and make this map of all these asteroids that you see. What you see here will be multiplied by about a factor of 100 when we're done. So stepping back, you know, what is the big picture here? The big picture is that we're at a new age right now where we as a species can think about going out there, mapping everything, mapping 1 million objects or so, flying around the sun, and we are talking about someday, should one of these be on a collision course with the Earth, actually deflecting it. So that's the big picture. Now let's zoom back in here and take a look at, again, what really this is all about, which is protecting life here on our spaceship Earth. What we want to do is get people to think of this as a spaceship and to think of themselves as the crew on board this spaceship, not just passengers. And we think there's really nothing more important than the long-term future of humanity.
So this was produced by the California Academy of Sciences. They used real orbits and real objects and did a spectacular job, I think. So obviously asteroids are a threat. They have impacted the Earth in the past, and some of them can do a lot of damage. The Meteor Crater one in Arizona, I don't know if you've seen that, but it's just off Interstate 40, and it's a fascinating thing. It's a little over 1 kilometer in diameter. It was formed by a 50-meter nickel iron asteroid. 50 meters is pretty small. It's very, very difficult to see such a small thing from the surface of the Earth. It has to be very close to us. But it caused enormous damage. It probably wiped out all life within 20 or 30 mile radius of that impact. And it was Meteor Crater that gave us the information. A guy named Gene Shoemaker in 1963 identified that had been caused by an impact. Some people had thought it was a volcanic feature prior to that. In 1908, there was a substantial impact in Combusken, Siberia, that was witnessed by people. Not many people in that area, fortunately. No known casualties, but it flattened trees over several thousand square kilometers. Turns out that this event was an airburst. The asteroid broke up in the atmosphere, high in the atmosphere, with an explosion of many kilotons of TNT that then created that shockwave that flattened trees and was very hot as well. And that was also in the range of 30 to 60 meter diameter object that caused that. It was not as strong as a nickel-iron object. But there are many other known craters. Here's a view from space of a crater in Canada. It's about 200 million years old. Most of the structure of it has been eroded away. But you can see clearly that there's a ring left over from it. That's a 70-kilometer diameter crater. It was probably caused by a several mile sized asteroid. And then the Granddaddy was the one that wiped out the dinosaurs. We now know that it landed in Yucatan Peninsula, Mexico, 65 million years ago. It was an approximately 10-kilometer diameter asteroid and created a crater. It's 180 meters across. And to quote Roger Linfield, this one 10-kilometer asteroid can ruin your whole day. So if you look across the surface of the Earth, there are literally hundreds of known impact craters. They're distributed. If you look at that distribution, you can see that there are a lot of them in Australia because there's a lot of vegetation and there's not a lot of weathering removing the evidence of the craters. But there are other places like Central Africa where it's covered with vegetation and a lot of weathering to erode the structures, and so there aren't as many known there. Also, it's not as populous, hasn't been studied as well. But we know that there were a lot more craters on the Earth over time, because if we look at the Moon, where there aren't the effects of erosion removing the craters, we just see craters pile on top of craters. It's a saturated crater environment, all from the same kind of impacts that we're worried about on Earth. Now, there were times in the past where the rate was much higher. Fortunately, we're not in that kind of a high rate. But we know quite a bit about the population distribution of asteroids, and what we have here, big asteroids are down here, and you can see here's a 10-kilometer diameter asteroid. So this is the one that wiped out the dinosaurs. It's this size. The size gets smaller as you go to the left, and there turned out to be a lot more of them. This is how many there are of each size, and it's roughly a linear power law distribution. The red line was how many were known in 2009. The red line is going up a little bit, but it's nowhere near this blue line. And you can see that if we look at events like Combusken, which is a pretty bad event, one that would wipe out the front range of Colorado, for instance, we're orders of magnitude, maybe 2 orders of magnitude, incomplete in our understanding of these objects, or we just haven't found them. So for every object we know that's 50 meters in diameter, there are 100 objects we've never seen at all. And any one of those could be the next impact. We've also got the impact interval in years here, and you can see that if you come across, and these circles are measurements, we think that there may be not as many as this theoretical prediction or empirical fit might have predicted, but in any case, there's somewhere in the order of a few hundred years between those kind of Tunguska kinds of events. So it's not going to happen tonight, with very much probability. But over the next 300 years, we ought to expect one of these things to happen. So it makes sense to do something about it. We have the decades of time probably to do the deflection if we find the object, but we need to go out and find these things and identify which ones pose a risk. A little bit of background: why do we have near-Earth asteroids that are threatening the Earth? And the answer is that there's a main asteroid belt out between Mars and Jupiter where there are millions, maybe 10 million, maybe more than that, asteroids. Most of them that we know about are very large, 100 kilometers, tens of kilometers. And they're out there fairly stable. They've been out there for most of the history of the solar system, maybe 4 billion years. They're very happy out there. They don't threaten Earth at all in general, but there are so many of them, and they react to the gravity of planets, Jupiter in particular, and Jupiter has cleaned out all of the objects that used to be here because Jupiter's gravity has kicked in somewhere else. And it's the ones that are still there are fairly stable, but every once in a while one gets kicked into gets kicked out of the main belt.
And,
sorry?
Where does that apply?
Oh yeah, I should tell you. This is distance from the sun. So Mars is over here, and Jupiter is off the chart somewhere there. And the higher it is, the more asteroids there are at that particular distance from the sun. So objects right here are in a resonant orbit with Jupiter. So every I don't know if that's the 2-to-1 orbit, but if that were the 2-to-1 orbit, then every two times this asteroid goes around, Jupiter's in the same place. So the gravitational pull of Jupiter tugs at it, and the pull builds up resonantly, and that sweeps it out of that resonant gap. So what happens with those main belt asteroids that get perturbed is that they are kicked out of that main belt. If they come into the inner solar system over a typical lifetime of 2 million years, 4 out of 5 are going to hit the sun. Most of the rest of those pick up energy and are kicked out of the solar system, but there's a residual 5% that have to find some other way to terminate their 2 million average lifetime. And some of those hit the Earth, some hit Mars, some hit the Moon. And it's the ones that hit the Earth that we're worried about. Now I want to talk a little bit about the spacecraft that you saw in the mission that was described in the movie. Our intent is to survey the near-Earth region for these near-Earth objects, NEOs, that have diameters greater than 140 meters. 140 meters is an interesting, not round number, but it turns out that it's about there are about 10 times as many 140-meter objects as there were 1-kilometer objects. And NASA took on a task in 1998 to find 90% of the 1-kilometer objects, and has completed that. So we now have orbits for over 90% of the 1-kilometer objects. But so the next step, in an order of magnitude sense, was to find 90% of the objects greater than 140 meters. What we need to do is not just know that the object is out there, but we need to know what is the orbit of the near-Earth object, so that we can predict in the future where is it going and is it a threat to Earth. When we find these 140-meter objects, some of them are going to be a long ways away. An object that's 100 meters but closer will show up just as brightly in our telescope, and we will then discover those 100-meter objects that are somewhat, on average, closer. And in fact, we can get down to the smallest size that can get through the atmosphere, which is about 30 meters. So we'll go from a lesser percentage, maybe half of the, say, 50-meter objects, up to 90% of the 140-meter objects. Once we know where these objects are and we know where they're going, we can in the future point our telescopes at them and learn a lot more about these objects. If there are some that look like they might get close to Earth, we can study them and follow up with ground-based telescopes and refine those orbits as precisely as we need in order to determine, is it a threat to Earth? And if it is, we can then worry about a deflection mission. So we'd like to launch in 2018, and in 6.5 years, we've reached the 90% completeness. NASA is participating in this mission. I'll talk in a minute about how we hope to do this, but NASA has signed with B612 Foundation a Space Act agreement that secures the cooperation between B612 and NASA and makes sure that this is a coordinated effort with NASA.
So you had to include detection of smaller NEAs there.
Yeah.
Does that mean like 50-meter objects?
Anything that's bright enough to trigger our detection algorithm, and that could be 30-meter objects if they're close enough. We retain all of the objects that we find because we don't even know their size until we have figured out an orbit for it. When we have an orbit, we know how far away it was. When we know how far away it was, we finally have an idea of the size.
But you're probably going to get a small fraction of
That's
50-meter objects.
That's right. If they're too far away, we don't see them. So our completeness is 90% on 140 meters and diminishes and is probably it's less than 50% on a 30 meter objects. So here's how we're going to do the mission. In 2003, NASA had a science panel that looked at what was the best way to find smaller objects that maybe couldn't be done so well from the surface of the Earth, looking through the atmosphere with its distortions and absorptions. And their conclusion was that a 50-centimeter infrared telescope in a Venus-like orbit was an ideal way to do this. And that's what we have adopted as our mission plan. What we do is we take an image of a large area of the sky, we find regions of interest around things that are moving, and we store those regions of interest. The reason we do this is to compress data, and I'll say a little bit more about that later. But we could not send down an entire picture because the telemetry rate just would not be nearly large enough over the large distances that we will be away from Earth. An important part of this, maybe a defining part of this mission from a programmatic point of view, is that B612 is raising the money to do this privately. Privately, we mean from philanthropic contributions from donors. And the fundraising has been going quite well. We've made a lot of progress. We've had some funded studies that we've done with Ball Aerospace. We've done a lot of work ourselves. We've managed to pull together a review team that's critically evaluated our plans. But this is all made possible through private donations. Ed Lieu, the CEO of this, when he retired from NASA, went to Google, and when he was at Google, people encouraged him to pursue this philanthropically, and they identify the cost of this mission as roughly comparable to a museum. In fact, the California Academy of Sciences that did that video was funded privately and is of the same order of magnitude of funding as are most museums or medical centers. And so this is an achievable goal, and we're making good progress towards it, but it's very different from the usual NASA approach of a contract that is funded publicly and then goes through NASA. B612 has selected Ball Aerospace to build and operate the mission. It was a natural fit, and I'll explain that in a minute. We will use a firm fixed price contract. That's an unusual development and an unusual approach in space as well. Commercial terms and conditions, what that means is that we tell Ball what we want. We think we're smart enough to tell them exactly what we want. They think they're smart enough to have priced it out so they don't lose money when they give us what we want, what we ask for. And it cuts out a lot of the open-endedness of a cost reimbursable contract where you sort of make it up as you go. And then, importantly for tonight, Ball will contract for mission operations and ground data processing with LASP. So there's a new step for Ball, and in that respect, in the relationship with Ball, I think it's a new step for LASP, because in the past, Ball and LASP have worked very closely together. You do lots of ground operations for them. But this time, LASP will do the science data processing as if it were a LASP science mission. So you know how to do it, but this time it's on contract to Ball and B612. The hardware we're flying is a 0.5 meter, 20-inch aperture telescope, so it's that big around, fairly modest. What's a little more challenging is that it works in the infrared. In the infrared, anything that's warm shows up as a signal. It's like trying to make observations at night in an observatory, and you leave the lights on, and it swamps the signal you're looking for. So we use an unobscured infrared telescope. Unobscured means there's nothing warm hanging in the optical beam. It's typical in visible light telescopes. You have a mirror, you have a first mirror and a second mirror that's right above it. But that in the infrared would be glowing, so we have to put it off to the side. It's called unobscured. The field of regard is the area that we use to search for these asteroids. So the telescope itself has a 5.5 by 2, whatever that comes out to, 12.5 square degrees field of view. But we move that 12.5 square degree field of view around over a 200 degree, so it's more than half of the sky every month. So we find all of the moving objects in that half of the sky every month. We have a 2 by 8 array of detectors, so there's roughly 25 megapixels. Passband is 5 to 10 microns. That's where objects that are at the distance of the Earth from the sun have their peak thermal radiation. So they're glowing on their own. They're not reflecting sunlight, but we're going to see, I mean, they do reflect sunlight, but in this passband, what we see is the emission from the object itself. And the important part of this is, as we showed in that movie, we're in a heliocentric orbit, means going around the sun, at 7/10 of an astronomical unit, 70% of the Earth's distance from the sun. And the advantage of that is it's like being on the inner track in a racetrack. The Sentinel telescope will be going around the sun much faster than the Earth. So these objects that we're worried about, which are somewhere out in the vicinity of the Earth, are going around the sun in something like a year, say. But we'll be going around the sun in much less than a year. And in fact, in 2.5 years, we will have lapped all the one-year objects. And so we'll have to wait for them to get close to the Earth, which is one of the handicaps of a ground-based observatory. So you can't see all the way across the solar system because these guys are so small. And if you have to wait for them to get to the Earth, it takes a long time. But if you get in that inner passing lane, you can see them within a couple of years. An important part of this, and one of the reasons that we went to Ball Aerospace, is that we were able to use, and they were able to use, a lot of heritage from the Kepler and Spitzer space telescope missions. Spitzer is an infrared telescope, much larger than Sentinel at 85 centimeters. It was also much colder. It used superfluid helium at 4 Kelvin to 4 degrees above absolute zero. Really cold. To do a very elegant infrared science mission, and it has been spectacularly successful, as has the Kepler mission on here. Kepler is a visible light telescope. It's 98 centimeters, almost 1 meter, and very large field of view, similar to what we get with Sentinel. Has a huge focal plane, 4 times the size of the infrared focal plane that Sentinel needs. And Ball has command of the infrared technology, low temperature thermal requirements, a large field of view, huge focal plane, all that data handling capability. Both of these telescopes, like Sentinel, left the Earth orbit, which adds all sorts of complications in terms of communications, power in your transmitter, how much data you can send down the link. So that actually has prepared Ball very, very well to understand what we need for the Sentinel mission. And then really, without these two, we would not be able to approach this mission the way we want to, which is that fixed price commercial contract. Given that we think we understand what we're doing, Ball is confident they understand what they're doing. This allows us to go forward with this new programmatic approach.
How are the stability requirements for Sentinel compared to what we have to do with Kepler?
We have we have, Kepler is far and away a higher point, it's more than an order of magnitude higher pointing stability requirement. We're comparable to the Spitzer requirement. Now Kepler did some things to achieve that we don't have to do, which is really good. So a few words about the configuration of the spacecraft and the telescope that we came up with. We're going to win down by Venus. Venus is 0.7, 70% of the distance of the sun, of the Earth from the sun, and as a result, it gets about twice as much heat input as Sentinel would if it were at the Earth. So we get a lot of sun on the sun side of the spacecraft. That's good for making solar energy, sort of, except that everything gets very, very hot. So in fact, what we do is we're going to have only about half of the solar array populated with solar cells, and the other half is going to be highly reflective glass trying to reject heat and keep things as cool as possible, rejecting heat back towards the sun. On the cool side of that sunshade, that's still not nearly cool enough for us, so we have two more layers of thermal barriers which intercept heat and radiate it out, and it radiates on this image, it radiates out, and that radiates down to the telescope, which can also radiate heat out. And this whole cascade of thermal protection should allow the telescope to run at about 65 Kelvin, so slightly colder than liquid nitrogen.
Are there batteries, or is the solar array sufficient?
There are batteries. We need batteries early on in the mission as we get stabilized, but we don't use them very much out here. Yeah, so this is continuously sunlit. We've actually angled the telescope so as we scan around the sky, the sun goes from perpendicular here to actually 55 degrees one way and 55 degrees another way. But in all those orientations, we generate enough power to run just off the solar arrays. Battery helps buffer the power system. So the telescope is 20 centimeters. I'll show you the design of the optics later. Here's some more thermal shields because the spacecraft runs at roughly room temperature, and we need to keep the heat from the spacecraft from getting up to the telescope, so it has its own shields. There's a large antenna that pipes the data back to it. Here's a diagram of the telescope. It's an off-axis, unobscured design. This is actually a fairly, it's a very, very good design for controlling stray light. It's what Ball uses on their Earth-looking satellites, where they get the whole Earth shining light up in here, and it causes all kinds of stray light. And what this does is it gives you, maybe see in gray here and here, it allows you to put in very nice baffles that reject a lot of the stray light. So this folded design is good for keeping stray light out and just allowing the field of view to get down onto the focal plane. So we have 3 power mirrors and a flat fold mirror in here that give us the configuration that we need. Say a few words about the how do we get in the orbit that we want. To get into most orbits, you have to take a great big rocket with you, and you head off the direction you want to go. And then when you get there, you have to brake, you have to stop and put yourself into that orbit. But actually, by using Venus, instead of carrying our propulsion with us, we use the gravity of Venus to slow ourselves down. So what Venus does is it reduces, if Venus wasn't here, this green dashed line would come right and be tangent right back here into the Earth's orbit, right in the same place. But instead, by using the gravity of Venus, we get into this red orbit, which is not circular, but we don't care. We're just going to be sitting somewhere in this orbit, looking back away from the sun, and moving around the solar system at a higher rate of speed than the Earth. Higher orbital period, shorter orbital period. So just from an artist's point of view, there it is with a purple track being how we get to Venus, and then in purple once we're there. Yes, if we didn't pay any attention and we waited long enough, we'd come back very close to Venus, but it will take decades for that, and turns out we won't be close enough to be a problem. So wherever we are, we're looking outward in this 200-degree field of regard. We can see 140-meter near-Earth objects out to the limit of this. If we drew the discovery zone for 30-meter objects, it would be substantially smaller radius in here, but we would see all the 30-meter objects in there. And so we will capture the 90% 140-meter objects that defines the mission requirement. I think I've covered this fairly well. So Sentinel is optimized for detection, and we have to keep remembering this because anytime you have a really nice telescope with a really nice focus plane, you get really nice pictures and you can do all sorts of things. But every one of those things is a distraction in the sense that it adds more complexity to the mission, it adds more data processing, and so we are keeping the blinders on. We're flying a mission that's going to find 90% of 140-meter near-Earth objects. And anything else that gets sent to ground with that system is great for us, but we are not doing what a science mission would do with this telescope. We're a NEO discovery mission. So we don't send the full picture down. We send 5 by 5 regions of interest. So we send the pixels around each moving object. And an object itself might fill up a 2 by 2 square of pixels, and we get the data around it, plenty of data around it, so we on the ground can understand exactly what we had at that point in our image. But we don't send down any of the neighbors unless they have a moving object. We reject a lot of false alarms by having a signal to noise ratio. That means that we have some background noise and we don't pay attention to anything that isn't 5 times more of a signal than we would get randomly from the background. So that too, if we set down a signal noise ratio of 4, we would have a higher telemetry rate, and we would need a bigger antenna and more power. And signal noise of 5 gives us our 90% goal. So this reduces the processing. This reduces the downlink data to a manageable level, and then we leave a lot of the work to be done on the ground.
Seems like you have to have some onboard processing to compare adjacent images to detect something that's
Yep.
moving.
I'm going to talk about that. So how do we figure out what is a region of interest? And to us, a region of interest is a place where a NEO is, or a place where a NEO was an hour earlier. So we have a scheme. If we take, say, this example asteroid, on day 1, we look at it 2 times, an hour apart, and we do that for the whole sky. So all these guys are at some point. So on the first day, we get a pair of observations that are separated by 1 hour. We store both of those images in memory, and we let the computer go and compare the 2 images. And we used to call that blinking when you did it optically. And Clyde Tombaugh, when he discovered Pluto, had a special gadget that would first display one photograph and then display the other. If you got the brightness and the alignment just right, the 2 would blink back and forth, and the stars would all be in the same place, but the guy that moved, Pluto, would jump back and forth from one frame to the other. And we'll do that in the computer on these 1 hour pairs, and we'll flag as a region of interest where the object was here and where it was here, but we'll also keep the piece of the image where it isn't, so that we can compare very in detail the location before and after on 1 hour intervals. And then 2 days later, we'll come back. We're going to go and do a good fraction of the sky, about 10% of the sky in 2 days. And then we're going to come back and do that same region again in a 1 hour pair and see where the moving object here got to. And so we'll have a point here, a point there, a point there, a point there, and that will start to give us this orbit. And we do that over the full 200-degree field of regard that we have. And 26 days later, we'll have done the whole 200 degrees, and we'll found all these guys. And we're ready to come back and do another set of 4 objects, 1 hour pairs, 2 days apart. And we build up another piece of the orbital track. And in general, we'll have an object in our very large fan of view for about 4 or 5 of these 26-day intervals. So we'll have an orbit that goes out the door there, and we'll be able to reduce the uncertainty of that orbit such that we should know, we should have good enough information that we will eliminate as a threat to Earth almost all of the objects that we find. The ones that we can eliminate, we'll follow up with ground-based telescopes.
Will solar energetic particles, for example, cause backgrounds in the pixels?
Absolutely. Absolutely. Cosmic rays will cause a lot of noise, and we will. I've got a comment about that a little bit later. Here's that equivalent of finding Pluto with photographs blinking one against the other. If we have 2 images taken an hour apart, and we look at an object, say, that's in B1 here and B1 there, and it didn't change, so we don't send the data down. There was nothing in A1, so we don't send it down either. Here's a star. It didn't do anything different, so we don't send it. But here is the NEO, and it was here on this frame, and then A3 over here doesn't have anything in it, so something changed. We don't know what changed yet. Maybe this was a cosmic ray. We just don't know. But in any case, we're interested. It roused our curiosity, so we put it in our memory to send down to the ground and think about it harder on the ground. And the same thing is true. There was nothing here in B3, but over here there is something in B3, so we send that down. And we send this box and this box as a pair, and we send this box and that box as a pair as well. And then, just so we know where we're pointing, we have a catalog of astrometric reference stars to tell us what part of the sky we're looking at, so that when we figure out where it was precisely, we compare it to where this star is, and we have very good measurement of its location.
We're going to talk about the scan pattern.
I have some charts about that, but there are many ways to do that. And in fact, I showed that we'd be in 1 hour pairs repeated after 2 days and after 26 days. That is a nominal approach, a nominal cadence for our observations, and we're still looking at that as.
But obviously, the field of view of the telescope itself is much smaller than the 200 degrees.
Right.
That you intend.
Right.
So is it a stop and stare?
Yes, it
for a while?
is.
Stop and
Yes, it is.
stare.
Let's see. After we've made this point right here, we take our field of view and we go 15 different settings in an hour. So 14 other settings. Then we come back and do the same piece of sky an hour later, and we do that for all 15 settings. That took 2 hours to get 2 measurements on 15 different placements of our field of view. And we do that for 12 more times. I'm sorry, 24 more times, and then we come back and do it. But the exact sequence of that is probably not critical, and we'll improve it later.
Coming back to that other diagram that you just showed, now the other one. Yeah. Once you have this orbit going out the door, that's on board, is that right? Did you have that
No,
information?
no.
That's
All
what
we
I'm trying to
did, we
understand.
snip out a region of interest around this point and send it down. So
Send that
all
down.
of this calculation is already done.
That's done on land, and then you.
Yeah.
What's the grid size on that diagram?
This is totally notional.
Is there any pointing of the instrument itself, or is it all done by spacecraft attitude?
The instrument is rigid to the spacecraft. The spacecraft uses star tracker to repeat very accurately, so the 1 hour pairs are registered with each other.
And we'll have a chance for questions at the end of the presentation, so just ask you to hold on. We'll let everyone get through this.
I think that might be good. So Roger Linfield at Ball has been running a model that he put together, a very clever model that simulates what the full field of asteroids like the movie had when it was The screen is full of green dots. And then Roger simulates the Sentinel spacecraft, and we get a prediction of how complete over time, here's the completeness, we can get with this 50 centimeter telescope. And after 7 years, we're not quite at 90% of 140 meter objects. We're not quite at, maybe at 60% of the 60 meter objects. But if we know that the ground-based observatories are looking at this as well, and it turns out that if we just have a simple, this is an existing Pan-STARRS telescope that is doing NEO searches right now, and if they just keep doing that, we will cross the 90% of 140 meter objects in something like 6 years. And that will have achieved our objective. So here's what's going to be done at LASP. So in 1 hour we get 15 tiles on the sky. In the second hour we get another 15 tiles on the sky. We put them into processing on board the spacecraft, where we compare. Actually, each one of these images is a stack of 6 30-second exposures. So we compare those 6 30-second exposures. If we had an energetic particle that created a false alarm, it will be in one of those 6, and it won't be in the other 5. So on board, we compare those 6. We find which are the transient events due to noise. We get rid of that. We find with some limited number of false positives, we find the moving objects, and we expect, given the curve I showed you of how many NEOs might be out there, that we have maybe 25,000 objects in each one of these frames. And so we'd have 300,000 moving object detections in a day. And then just because we don't know where all the noise is, we double that for false positives, and to sort of size our memories. So that comes to the regions of interest and come to the ground. In 2 days, we cover a whole zone of that sky. We compress it. And so here's coming to the ground. We get about 3 gigabits per week. It comes through the Deep Space Network, which is available to us through the SpaceX agreement. And so the regions of interest come down here to the Sentinel Data Center at LASP. What is done at this, well, and then from here we send, and I'll explain the tracklet in a minute, to a NASA operation called the Minor Planet Center, where all of the asteroids that are known are cataloged. In fact, they take observations of asteroids before we know what the orbit is. If we're pretty sure it's a moving object, we send it to the Minor Planet Center. They're able to combine all of the moving objects that they have in their database and compute the orbits very precisely, and then it gets archived in the JPL NearEarth Object database, where JPL also does the calculations on what's the threat potential. But back at LASP, then, what do we do? The Science Data Center. So operations, I don't have on this chart, but mission operations commanding, getting the data back down is the LASP responsibility, but LASP is also the data center. So what happens there? LASP will take the regions of interest that come down, those 5x5 areas where the satellite thought something was going on there. LASP will take a look at those pairs and vet those observations to see if it looks like it was an asteroid, and if it's close enough so that it's physically plausible that it could have moved from here to there in 1 hour. So all of that kind of screening will be done, obviously routinely, on 300,000 objects a day. This will all be automated. But that will turn into where it was at time 0 and where it was at 1 hour later, the vector that connects those 2 points we call a tracklet. And we don't send every one of those tracklets to the Minor Planet Center, though, because some of those are going to be spurious, or we will have connected it to the wrong object. We'll have object A in the first image, and we'll mistakenly think it was object B in the second image. So what we do is we wait for a 2-day pair, where we get 4 objects that are all falling on a single line. And then we say, okay, we are now able ourselves to create a more or less useful orbit out of these tracklets. So we send the pieces of that orbit to the Minor Planet Center, where it gets put into their database, and they calculate the orbit with all the pieces that they might have, that we might assume. So we do candidate orbit calculations here at LASP, but we don't calculate, let's say, the official orbit. We calculate orbits to screen tracklets that we want to send to the Minor Planet Center. So we will have found asteroids, we will have gotten enough data on them to predict where they are, perhaps as much as 100 years in the future, so we can look and see is anything out there going to hit Earth in 100 years. If not, we're all happy. We have 500,000 objects that we can go study with our telescopes and do a lot of great science with it. We will have also as many as 100 times as many NearEarth objects as we know now, so that these will be targets for low-energy rendezvous for human and robotic missions. So what's the problem with humans visiting an asteroid? The problem is most of these asteroids are going really, really fast when they come past the Earth. And with a chemical rocket, you can't match speed with it. Play around with it, look at it, get some samples from it, then get back in your spaceship and get all the velocity necessary to get back over to the Earth. So you have to find one that's just coming by real slowly. And right now there are maybe 3 or 4 in the next 38 years that NASA could imagine having a rocket big enough to get to it and get home again safely. So 3 or 4 in 30 years, if we could do 100 times as many, which is what Sentinel will do, down to 50-meter objects, instead of being 3 or 4, it'll be 300 or 400, so it'll be more like 1 a month than 1 a decade. And the same is true for science missions. We'd love to be able to go park a robotic science laboratory on an asteroid, just like the Curiosity rover on Mars right now. But we can't do that if it's going so fast that we can't match its speed. Okay. Yeah.
Your observation plan seems to depend on some degree on orbits being somewhat circular. I can't really tell how circular. What's known about the density of objects versus eccentricity, and how eccentric an object can you detect in this plane?
Good question. I didn't mention it, but we know about a total of over 9,000 near-Earth asteroids right now. So that 9,000 gives us a pretty good statistical sampling of what kind of orbits they are in. And so we have a good idea of the eccentricity and inclination, orbital periods, centimeter axis of those objects. And it was exactly that distribution of orbital parameters for that 9,000 objects that went into the predictions of completeness here. So we actually created 500,000 objects, but they had the same distribution of orbital parameters as the 9,000 known objects, corrected maybe for some observational bias. And it's against then that real life expected distribution of orbital elements that you get from that. So that's a good question, but we have accounted for it.
A similar question, is the 26-day observation sufficient for most of these orbits to nail the orbit so that you don't have to keep track of it after that?
26 days gives us a reasonable orbit such that we would be able to distinguish that object from all other of the 500,000 near-Earth asteroids that we're going to find. So we'll be able to give it a name and an identity from that 26-day period, but it won't allow us to project its location forward 100 years. And so what we would do in that case, let's say it's a fairly faint one that gets out of range of our observatory after the 26 days. In 6.5 years, there's a good chance we'll see it again, and that's the point of this minor planet center, is that they'll keep all of those little pieces of arcs forever. And so if we or anyone else gets an object that has that same class of orbital parameters, we'll be able to make that connection and improve the orbit substantially. And if that 26-day piece of an orbit that we get suggests that it would come anywhere near Earth, we will follow up quickly with large telescopes on the ground to get ground-based measurements of those individuals that are both out of our field of view and possibly affected. Yep.
Yeah, the Sentinel mission is the detection mission. I'm wondering, is it a minor planet center that's going to do the forward integration? The orbital data, do all the perturbation work and all that stuff?
It's the JPL NearEarth Object Program Office that is NASA's center for doing that threat determination.
Have they committed any fund to do that?
Yes, they have. This task and this task are obligated through the Space Agreement, as is the Deep Space Network.
In one of your early slides, you showed a slight departure from the simple extrapolation. This one, I didn't quite understand what the basis of that.
It's totally empirical. It's just that we're sitting on the Earth and we're watching things go by, and now with the WISE mission and infrared telescope mission that flew a year and a half ago, they too don't see quite as many as that straight line prediction. So it's depleted for some reason, apparently, and we still don't have very good statistics on it, but it looks like it's maybe depleted by a factor of 2 or maybe 3. Absolutely. Yeah.
Are you looking at ways to possibly nudge it out when it's orbited if it appears to be?
B612 worked on 3 techniques for deflecting an asteroid. What everyone had just said, there has to be a big enough nuke that we could break it up. Turns out you don't want to break up one of these things, because then you have 2 or 3 or 4 or 5 of them. And they're probably all still going to hit the Earth, because you didn't move them very far, you just fractured the object. So that's not how you use a nuclear bomb. What you do is you put it next to the asteroid, and the pressure of the explosion will move the whole thing a little bit, maybe a millimeter per second velocity put into it. Another way to do it is to run into it like the Deep Impact mission demonstrated. So you get a few ton spacecraft, and you get very high velocity, and kinetic energy goes as velocity squared. So you can actually put a few millimeter per second velocity change into a small asteroid, 100-meter asteroid, with a couple ton spacecraft. So very, very much demonstrated already by NASA involved. And the third technique was one that B612, Ed Liu and a couple others invented, which is called the gravity tractor. And this is one where you fly out with a couple ton spacecraft. You stop, you hover right over the spacecraft, maybe 100 meters off the surface of the spacecraft. And you're kind of like a yo-yo. You let the gravity of the asteroid pull you in, then you fire thrusters. You don't impinge the plume on the asteroid, but you lift the spacecraft back up so it doesn't hit the asteroid, and you just hover there then for a year or so. And that too put about 1 millimeter per second into an asteroid. And 1 millimeter per second times a year is 30 million seconds. So now you're 30 million millimeters away from where you would have been otherwise, right? And if you do that for 10 years, you're 300 million millimeters away from where you would have been otherwise. And it's just a matter of time, and you move the asteroid by the radius of the Earth, and it's a mess.
So you're talking about 100-meter asteroid.
Yeah. Yeah.
Going back to this gentleman's question, over a long-term period, how is the Sentinel powered to adjust itself over time? Is it retro thrusters or?
There are, in the spacecraft, there are momentum wheels that are gyroscopes, basically, and by speeding them up or slowing them down, the wheel would like to stay the same speed. And if you put a little brake on it, you start turning. And then when you get turned as far as you go, you speed the wheel up again and you stop. So it's almost all done with those momentum wheels. There is some pressure from the sun, the radiation pressure from the sun, and some other external torques that will eventually speed those wheels up, and so you use thrusters to keep the speed of the wheels in the nominal range.
Of the 9,000 known NEAs, what's the maximum inclination to the ecliptic?
I don't know the answer to that, but it's very close to 90 degrees. The distribution, because these things are out in the asteroid belt, the main asteroid belt, they're fairly concentrated in the ecliptic plane because they're in long-term stable orbits. But when they get disturbed in every direction, so that there's no real reason why they couldn't be 90 degrees. And it's more spherical, much more spherical distribution than the asteroid belt.
But you're only looking plus or minus 55 degrees, right? So.
No, let's see, where is that picture? Where did it go? That's the artist's picture. This is a 100-degree half-angle cone. So I've just shown the cut in the ecliptic plane of that cone, but it is circularly symmetric about this axis right here.
Okay.
It gets it gets that by rotation.
You're looking like this.
Yeah. So it's a 100-degree half-angle cone that we have access to everything inside it. Yeah.
So you must know that you're not going to overwhelm the land-based telescopes with candidates, so that you have to have figured out what uncertainties on orbits you need to have to do that. And I know.
You give us too much credit. You give us too much credit. I don't know. You know, the nature of asteroid threats are when you find an asteroid and you've got a very poor orbit for it, so you know it's headed in that direction, but it's in a really big angle, and the chances of the Earth being somewhere in that great big angle are pretty good. You know, so then you need to get another observation, and the angle goes down smaller, and pretty soon the Earth isn't included in that possible range of places it could go. But at the outset, there's very low probability because the angle's really big, but it could go anywhere in there. And I don't think that Earth-based telescopes will get excited about the ones where we don't have a very good orbit for it yet.
Exactly.
But when we get an orbit 26 multiples of 26 days, and it still has the Earth in that ever shrinking cone, is when the telescopes will crank up. Now, I've got to say there is a huge level of activity in the amateur astronomy community. People with what to me were professional telescopes when I started this out, who have these wonderful CCD cameras and spectacular software and great big 36-inch telescopes or something, and they're out every night looking. They look at what the Minor Planet Center has in its database of candidate objects, and they go out and get measurements of those objects. It's not hard to see. If you know where these things are and where they're moving, you can track them with a modest-sized telescope and integrate long enough to find them. It's the discovery of them that's the hard part. So we'll do the discovery and we'll follow up on the ground has been much easier. But we could get our own ground. They will look at the highest priority ones first until they're exhausted. Anyone else? Oh, I'm sorry, I'm missing something. Yeah, thank you.
Couple things. How do you have a filter that gets you down to just infrared light, or I didn't see it yet?
The detector cuts off at the long side, the 10.4 microns. The detector does that. On the shorter side, I don't know that we really need to cut it off at 5. If we have good sensitivity at 4, it'd just be more photons for everybody. So no, it's pretty much wide open.
So are you steering to get downloads to the Earth?
Yes, we have to. We have a steerable antenna, but it can't. It's only. It's not sufficiently articulated to find the Earth from every location. So it's got one axis of control. We need to turn the spacecraft to put the Earth within the reach of that one axis. So we lose about 3 hours a week during our downlink.
And then, how much, because the optical properties of what you're looking at, the asteroid you're looking at, change. So you think if it's a nickel iron, it's going to be very different than a rock. Plus, they orbit, so the optics changes with time also.
There are things going on there. The shape of the asteroid, they all rotate, and there aren't very many round ones. And so their brightness changes depending on whether you're looking at it broadside or end-on. And then there are, in visible light, there are some really dark asteroids, low albedo, 4 or 5% albedo, and some modestly brighter, like 20%, 4 or 5 times more reflective. But in the infrared, we're looking at the emission that comes from these things. And so the variability caused by the composition of the asteroid itself in the infrared is not a very large range. So the brightness will correlate to the area that we're looking at, but we still could be looking at the end of a cigar or the side of a cigar. We won't know that right away, but as we build up more pieces along the arc, if we see the brightness vary, we'll know it's an elongated rotating object.
Yeah. Back to eccentricity, it sounds like in your sample, I think you said 9,000 known objects. Probably not too many of them are eccentric enough to go out as far as the Jupiter.
Well, they almost all have aphelia that are out in the main belt. Okay. The great majority of them are still, they've been perturbed once, which has lowered their perihelion, but has left their aphelion about where it was. It takes a second encounter to lower that.
So you're likely to see them in 6-7 years.
That's right. So what typically we'll catch them when they're near perihelion, close to the sun, close to the spacecraft. Then as they go along in their 4 or 5 year orbit, they will stretch back out in the outer solar system when they're too far from the sun and too far from the telescope. But then they'll come back, and we'll be waiting for them, and we'll have salted away the earlier observations so we can piece it together. It's called a recovery. It's very good.
So some of the algorithms that we're using now on Kepler might be helpful in recovering orbits,
well,
or recognizing that you're seeing the same thing again.
Very possible. We haven't looked at it that way, but it's the same sort of statistical analysis and period folding kind of thing. Okay.